Welcome back to the second part of our lecture on the binomial distribution. What we're after is figuring out the probability of getting a certain number of successes when I try something over and over again with a fixed probability of success. And we're going to base this on the fact that independence number allows me to multiply probabilities as we introduced in the first section. So suppose I have two coins, a brown coin and a green coin, so I can tell them apart. And I flip the brown coin and it comes up heads. Well, what might happen when I flip the green coin? Well, it might come up heads, or it might come up tails, while the brown coin is still heads. So these are two different results, right? Heads on brown, then heads on green. This is heads on brown followed by tails on green. Now there's more things that can happen, right? I can have tails happen on the brown coin, followed by heads on the green coin, and finally tails happening on the brown coin, while tails happen on the green coin. So I have four different outcomes, four different patterns that can happen. And if I count the number of heads, let's do that here. You can see that here I have two heads, here I have one, here I have one, and here I have 0. So we can make a little table then of two things. The number of heads, and the number of ways, or the number of patterns, or the number of outcomes that contain that value. So if I start out with no heads, how many different patterns have no heads? Only one of those. If I ask for how many different patterns have one head, well, this result has one head, and this result has one head, so there's two different patterns that contain exactly one head. And of course, with two heads, that's the only other possible outcome. There's only one pattern that contains that. So this table is kind of a frequency count, almost like a histogram. How many have one? How many have two? This is my frequency, and this is my count. Okay, well, this is pretty easy, but it brings up a point. If I now I can ask two different questions. What's the probability of getting the exact outcome, heads, tails, for a fair coin? Well, that's the probability of heads times the probability of tails, and we'll assume the coin is fair for now. That's 0.5 times 0.5, or 1/2 times 1/2. That's a quarter. But for this different outcome, the probability of tails then heads, that also has exactly one heads in it. That, by definition, of my license to multiply is the probability of tails times the probability of heads. And that's, of course, the same, because I'm multiplying the same numbers. That's also recorded. So I can ask the question in a different way then. What's the probability of getting one head out of two? Well, one way I can think about it is to add these up. But the easier way to think about it, since the probability here is always going to be the same, it's 2 times 1/4. Because there's two different ways I can get exactly one heads. I could do it from here. 2 times 1/4, which is, of course, 1/2. So 50% of the time I'm going to get exactly one heads in this experiment. What we'll do next is we'll go to 3 different coins and see if we can start to develop a bigger pattern here. So now I'm going to introduce a blue coin. And it could be, for example, all tails in each of these cases. But now I'm going to need more space to do this right, so I'm going to erase my table. Because the other thing is the blue coin can turn up heads. So I'm going to erase this all and start writing a little bit smaller so we can fit all the possible results. And I'm going to do this in maybe a different pattern. I could get heads or tails, heads, tails, heads, tails, heads, tails. On the green coin, with each of these I could get heads or tails or heads or tails. And now on the red coin, the blue coin, excuse me, brown coin, we'll get it right. Heads, 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 tails, 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 tails. Now you should convince yourself that we've got all the different possible outcomes here. And how many different outcomes do I have? 1, 2, 3, 4, 5, 6, 7, 8. That makes sense because I have two choices for what happens to the brown coin, times two choices for what happens to the green coin, times two choices to what happens for the blue coin. So I have 8 different possible results. 2 times 2 times 2. And now let's do the counting game again. The number of heads and the frequency or the number of patterns that contain that. So since I've flipped 3 coins this time, I can either get no heads, or 1 heads, or 2 heads, or 3 heads. Well, how many different patterns have no heads? Well, it's only this last one. Tails, tails, tails. Everybody else has at least 1 heads. So there's only one pattern that contains no heads as the result. How about 1 heads? Well, starting from the bottom, this one has only 1 heads. This one has only 1 heads, and there's one more here that only has 1 heads. There's 3 different patterns that contain exactly 1 heads. How about 2 heads? Well, again, starting from the bottom, this is the first one that has heads, heads. That's got 2. This one's got 2 heads, heads. And this one's got 2. There's actually 3 different outcomes, 3 different results, distinct results that contain exactly 2 heads. And there's only one, all heads, that contains 3 heads. So now if we ask about the probability of getting 2 heads out of 3 tries. Well, again, I can pick any one of these, like the probability of heads, heads, tails. With my fair coin, I know that's going to be 1/2 times 1/2 times 1/2, or 1/8. But how many different ways can that happen? Well, it happens. 2 heads happens 3 different ways. So this answer isn't just this one, but it's 3 times 1/8. Because there's 3 different patterns that all have the same probability, 1/8. Heads, heads, tails, heads, tails, heads, and tails, heads, heads, right? Those 3 different patterns all have the same probability, 1/8, so I multiply 3 times 1/8, and I get 3/8 as the probability of getting two heads out of 3. Notice this time I didn't have to go hunting for the patterns, I just used the counts. How many different ways does it happen? How many distinct outcomes have 2 heads? And so I just multiply the 3 times the probability of getting 2 out of 3 heads in one particular way. All right, let's see if it still works if I go to an unfair coin. See if our pattern of work still holds. Suppose now that I have an unfair coin where the probability of heads is 0.6, so the probability of tails is 0.4, And I want to ask the same question now. What's the probability of 2 out of 3? Well, I need to figure out the probability, the basic probability of one of these patterns. Again, probability of heads, heads, tails will work as one of them. And that's now, by my multiplication of probabilities, 0.6 times 0.6 times 0.4. Which we calculated before, but we can calculate it again. 0.6 times 0.6 times 0.4 is 0.144. But that only accounts for this way. But there's 3 different ways it can happen. So this answer is actually 3 times 0.144, which is 0.432. So with this unfair coin, I have about a 43% chance of getting 2 out of 3 heads. Okay, but this could get pretty tedious. If I throw 5 coins, listing all these patterns seems kind of crazy. An interesting thing developed by a mathematician of the 1600s, I'm going to draw it now, that lets me do this counting without actually listing all of the possible patterns. It's called Pascal's triangle, after Blaise Pascal, and it starts out with this pattern, where this row corresponds to 2 tries. That is like flipping, corresponds to 1 try, like flipping 1 coin. That is, there's only one way to get heads and one way to get tails. If I flip 2 coins, his next row goes like this, where I always start with 1, but then I add the results of the 2 diagonally above. This corresponds, remember, to our first result. When I flip 2 coins, there's 1 way to get all heads, 1 way to get all tails, and 2 ways to get 1 of each. So if I flip 3 coins, following our pattern, I start with a 1, now I add those 2 numbers. 3, I add these 2 numbers, 3, and then I bring down 1. This is, if I flip 3 coins, there's 1 way to get no heads, 3 ways to get 1 heads, 3 ways to get 2 heads, and 1 way to get 3 heads, as I found here when I counted the patterns. What would the next row be if I flip 4 coins or do 4 tries? Well, it's 1, 3 plus 1 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and I bring down my 1. So this says if I try something 4 times, there's only 1 way to fail every time. 4 ways to get 1 success, or 1 heads, 6 ways to get 2, 4 ways to get 3, and 1 way to get 4. But what if I do it 5 times? Well, again, I bring down my 1, 4 plus 1 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and 1. So this gives me the pattern for how many ways I can get no successes, 1 success, 2 success, 3 success, 4 success, or 5 successes out of 5 tries. So, for example, using this thing, if I wanted to know the probability of 3 of 5 successes, well, the number of ways would be, that's none, that's 1, that's 2, that's 3. It's going to be 10 times the probability of any one of those patterns. So it gives me a way of looking up directly those numbers. Well, this is okay for small examples, like up to 6 or 7 tries. What if I try something 100 times? I certainly don't want to make all 100 rows of this table. That would be ridiculous. So, fortunately, someone came up with a formula that lets me compute the number of patterns. And it goes this way. The number of ways, or number of patterns, for getting k successes, we can think of those as heads, out of n tries, the total number of coin flips, is, by definition, the following. There's the symbol, n choose k, and I compute it as n factorial over k factorial times n minus k factorial, where we, n factorial. Well, that looks like a mess, but let's show how it works by example. Suppose I want this one that I computed before 3 out of 5. How many different ways can I write down 3 successes out of 5 tries? Or how many different ways can I write down patterns that contain 3 heads out of 5 attempts? Well, by this formula, it's 5 factorial divided by 3 factorial divided by 5 minus 3, 2 factorial. The bottom ones always add up to the top one. Well, what does factorial mean? You may have not seen this before. When I say factorial, I mean multiply all the numbers down from that point. 5 times 4 times 3 times 2 times 1. That's 5 factorial on the top. What would be 3 factorial? Well, it's 3 times 2 times 1. And 2 factorial is 2 times 1. Now notice I've got 2 copies of this. 3 times 2 times 1. Just for arithmetic now, I can cancel those. And that's 5 times 4, that's 20 divided by 2 times 1. And that's 10. And that's exactly what we found in Pascal's triangle. Now even this is a little ugly to work with. It turns out our calculator knows how to compute this idea of how many different ways can I get k successes in n tries. So I'm going to erase Pascal's beautiful triangle. And the calculator function that does this work for us without having to do all this ugly arithmetic, is the function NCR. And the way we use it is we put in the number of tries first, in this case 5, and then we elicit the NCR function, and then we put in the number of successes we want, 3. And what it tells me is the number of ways. It tells me this so-called binomial coefficient, which is the number of ways it can happen. So let's go to the calculator screen, just so I can illustrate this in a couple of examples. So if I want to know what the third entry in the 5th row of Pascal's triangle is, that is, how many different patterns of length 5 have exactly 3 successes in them. Here's one way. Using heads as my successes. Heads, 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 tails, tails, right? That's one way it can happen. If I want all the ways it can happen, I type in 5, and then I go to the math button, math, over to probability. It's a menu, so I cursor over to probability, and notice it's the third one down. NCR means how many combinations, essentially, is what the C stands for. So the big number, number of tries, NCR, the number of successes we want to compute, and it gives me the 10. So this is really handy when we do something much bigger, like what's the probability, what's the number of ways of getting 16 successes out of 30 tries. That would be 30 times 29 times 28. It's a mess to calculate, but the calculator can do that very simply with 30 NCR 16. I'll illustrate that. 30, math, probability, the third one down, NCR, and 16, and it's a big number. There are 145 million, 422,000, and 675. That is, if I try something 30 times, there are that many different patterns of length 30 that contain exactly 16 successes, or that contain exactly 16 heads, if I'm thinking in terms of heads and tails, and we certainly wouldn't want to list that out to get that number. Okay, let's put this all together now into our binomial distribution and actually do a worked out example. First, I'm going to suppose that my probability, I'm going to change from heads and tails to successes and failures, because it could be something much different from coin flipping. And I'm going to say the probability of success is just some number p. Remember, it's a probability, so it's between 0 and 1. If that's my probability of succeeding, then my probability of failing must be 1 minus p, because I either succeed or fail. So if this is 0.6, that's got to be 0.4. If this is 0.9, that's got to be 0.1, because the total probability adds up to 1. And if I don't succeed, then I fail. If I don't fail, I succeed. They're complementary events. So given these conditions and independent tries, then the probability of getting k successes in n tries, that's shorthand for that, is, first of all, the probability of this happening. Well, what's the probability of getting k successes? Well, if they're independent, it's p times p times p times p, k times. This is p to the kth power, because probabilities, like one of these patterns that works, is going to have k s's in it, and it's going to have 1 minus n minus k p's in it. So then I multiply by the number of failures. Well, the number of failures is going to be n minus k, because I tried n times. So if I try 20 times and I am looking for 5 successes, then there must have been 15 failures. If I try 20 times and I'm looking for 16 successes, there must have been 4 failures. And this is simply the probability of failure. So this will let me calculate the probability of success, 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 where there's exactly k of these, and then fail, 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 where there's exactly n minus k of these. But we also have to take into account that this isn't the only way to get k successes in n trials. How many different ways are there? Well, there's n choose k ways, or in other words, n NCRK ways of that happening. So this is my binomial formula. Let's use it for one example. Suppose I have the following, that I've got something I'm trying and the probability of success is 0.52, like my fraction of my voters that's going to vote for a certain candidate. Then the probability of failure, that is the probability that they won't vote for the candidate, if that's my context, is going to be 1 minus that, which is 0.48. Now we can ask for the probability of 7 of 16. That is, if I take a sample then of 16 voters, where the probability that they belong to that candidate is 0.52, what's the probability that exactly 7 of them will be a success or vote for that candidate? Well, I can use my formula. I need 16 choose 7. That's the 7th entry in the 16th row of Pascal's triangle. Or I can compute it as 16 NCR7, that's how we'll actually find that number, times the probability of success, which we said is 0.52. How many? 7. Times the probability of failure, 0.48. Well, if I have 7 out of 16 that are successful, I must have 9 out of the 16 that are failures. Now notice something about these numbers. The two probabilities will add up to 1 because it's success and failure. 0.52 plus 0.48 is 1. And the exponents will add up to the number of tries. 7 plus 9 is 16. Now all I need to do is use my calculator to work these out. So what do I do?
Oh, wait.
first thing I want to compute is the number of ways this happens. That's, and I put it in parentheses, 16, math, probability, NCR, 7. That's the number of ways. That's my 16, choose 7. And I multiply by 0.52 raised to the 7th power. That's my probability of success, raised to the number of successes, times 0.48 raised to the 9th power. That's my probability of failure raised to the number of failures. And I get an answer, which is 0.1591, rounded to 4 places. So I have just about a 16% chance under these conditions